Hello everyone and welcome back. In the last few discussions we've been discussing the linear combinations of different types of random variables, for example normal, chi-square, f, and t. And we've also been talking about, some special PDFs that are associated to each of those random variables. For example, the standard normal, possibly even the gamma, the exponential, the uniform distributions, and so on. We've also been talking about the interactions between these variables, for example, how to use the covariance and the product moment to determine whether two or possibly more events are independent from one another. And now we're going to be taking those discussions and now talking about how these random variables and their distributions can be used to applications of statistical inference. So let's just talk about a couple things that you probably are already familiar with. So let us suppose that we want to estimate the mean of the population, let's call it mu x. So if we're going to estimate mu x, we have to choose a particular metric that is going to be useful for us. So recall how to calculate the mean of a population. So mu x is going to be equal to 1 over capital M times the sum from k is equal to 1 to capital N of each of the values in our population. Now, of course, if x is a random variable, then we can take mu x and call it e of capital X. And that means these xk's are also random variables as well, coming from this population. So one could, of course, ask, well, is x bar, which is going to be equal to 1 over little n times the sum from k is equal to 1 to m of xk, and keep in mind that little n is less than or equal to capital M, and the statistic is calculated from a sample that is drawn from a population, ideally simple and random, and each of the values independent of each other, but of course not necessary or sometimes not possible. But is this statistic, x bar, a good and unbiased estimate for mu x? And if it is a good and unbiased estimate, is there some error that it inherently has when we're using it to approximate mu x? So we're going to be looking at this and a couple other metrics in a little bit of detail in this discussion. So first off, is it a good estimate for this parameter mu? Well, clearly we're dividing by some number. We're summing up all the values. So it's technically the total divided by the size of the structure that we're analyzing. So technically in that regard, they are definitely, x bar is definitely a good estimate for mu x. Now, what do we mean by unbiased? So the formal definition of an unbiased estimator, so let's just give the definition. So a statistical random variable, and let's just call it A, is an unbiased estimate for parameter random variable, let's call it alpha, if the expected value of that metric A is actually equal to alpha. So this is more so a theoretical definition, and we can sort of explore how we can actually use this definition to actually prove that estimate, for example, x bar, is a good and unbiased estimator for the parameter mu. So let's just take a quick look at that, and of course we've talked about this before if you've been following along. So what is the expected value of x bar? Is this really equal to mu? So that's just going to be equal to the expected value of 1 over n times x1 plus x2 down to, say, xm. And keep in mind this 1 over n is just a constant. It can factor out. So that's just going to be 1 over n times the expected value of x1 plus x2 plus keep down to xm. So expected values can distribute over sums regardless of the independence between them. And we're just going to be left with 1 over n times the expected value of x1 plus the expected value of x2 all the way down to the expected value of xm. So since each of these values, x1, x2, and xn, are all coming from the same exact population, each of these expected values are going to be equal to the mean of the population that they're going to be drawn from. So that's going to be equal to mu x plus mu x all the way down to mu x. There's n of them in this exact sum, so that's of course going to be equal to 1 over n times mu x. These mu x do cancel, these n's do cancel, and we're just left with mu x. So therefore, the expected value of x bar is equal to mu x. That means x bar is an unbiased estimate for mu x, or just mu as some people say. So of course there is some standard error associated with that estimate because they rarely are equal to each other. Sometimes they are, it's definitely possible, but generally speaking there is some error associated to this estimate, especially if the sample size is small or the sample is not well representative of the population. So what is the standard error? So the standard error, so we can use the expected value to prove that this estimate is definitely unbiased. So the standard error is defined as the variance of that statistical estimate for this parameter. So what is the standard error for the estimate of x bar in regards to its estimate of mu x? So pretty much what we're asking is, well, what is the variance of x bar? So the variance of x bar is going to be equal to the variance of 1 over n times x1 plus x2 all the way down to xn. Again, this 1 over n is a constant. It can be quadratically factored out of the variance. Remember that property from the properties of variance. So we're going to be left with 1 over n squared times the variance of x1 plus x2 plus all the way down to xn. We can distribute variance over the sum of these random variables as long as we assume that these variables are independent. If they aren't independent, there's going to be some covariance terms in this. So let's assume that this indeed is true. So that means our sample is a simple random sample of all independent values. So if we have that, then we're going to have that this is going to be equal to 1 over n squared times the variance of x1 plus the variance of x2 plus all the way down to the variance of xn. Again, we're assuming that each of these values, x1, x2 down to xn, are coming from the same exact population. Hence, they have the same exact theoretical variance. So that's going to be equal to 1 over n squared times sigma x squared plus sigma x squared all the way down to sigma x squared. There's again n of these values that we have. So that's going to be equal to 1 over n squared times n times sigma x squared. The n's do cancel and you're just left with sigma x squared divided by n. That is the variance. This is not in the same exact unit as our measurements, so instead of defining the standard error as the variance, we define standard error as the standard deviation of the statistical estimate for the parameter that we're interested in. So therefore, the standard deviation of x bar, which we're going to be abbreviating by SE x bar, which is going to be shorthand for the standard error associated to using x bar as an estimate for mu x, is going to be equal to the square root of that term, which is going to be the standard deviation of x divided by the square root of m. Right? So is x bar an unbiased estimate for mu? Yes. And the standard error associated to using that particular estimate for this parameter mu is going to be given by the standard deviation of the parameter that you're drawing from divided by the square root of the sample sizes for these samples that you're drawing from. Also keep in mind, this x bar is going to be having some distribution. So the distribution of x bar is going to have a mean of the same mean as the population you're drawing from. The standard deviation that you're for this x bar distribution is going to be the same as the standard deviation of x divided by the square root of m. So those are two important properties about the distribution of this random variable x bar. Also, if x is normal, then since x bar is a linear combination of normal random variables, that means that x bar will also be normal. And also another interesting property, I guess this is a special property, if x is not associated to a normal distribution, then as n gets really large, the distribution of x bar is going to approach the normal distribution, which is pretty interesting. But again, that's the central limit theorem. If you don't remember what it is, definitely check out those concepts. So those are some things associated with x bar. So one could ask also, well, what about the variance of the population? Is there an unbiased estimate for the variance, and is there some standard error associated to that estimate? The answer is yes. So let us just take a moment and look at that and see how those theories play out. So now the guiding question that we want to answer is, suppose that we want to estimate sigma x squared and sigma x. Well, what are we going to use as an estimate for that particular population parameter? So one, of course, will guess that the estimate that we want to use is going to be the sample variance and the sample standard deviation. So let's just do a quick review of what those are. So remember, the parameter that we're going to be estimating here is the variance. So remember, the variance of x is defined to be equal to 1 over capital M times the sum from k is equal to 1 to capital N of xk minus the parameter mu x times the quantity squared. And keep in mind, this quantity is sometimes called the sum of squared differences for that population. So there definitely is a couple metrics that are hiding inside this other metric that we're describing. So if this is the case, and this is the thing that we want to estimate, one could ask, well, maybe we can approximate with the thing, let's call it 1 over n times the sum from k is equal to 1 to little n of xk minus x bar squared. So why not we use this particular object? Because we know that this is not the formula for the sample standard deviation or variance. Actually, the variance formula is going to be equal to 1 over n minus 1 times the sum from k is equal to 1 to n of xk minus x bar, the quantity squared. So why do we choose to use this as an estimate for sigma x? Because clearly these leading terms are not, I mean, of course they're not the same, but they're not even well, they're sort of similar, but because n and capital N are usually not the same. But they're definitely intrinsically different, right? So why not use 1 over n instead of 1 over n minus 1? Like, why is this one the preferred one over this other discussed one? So the question that we need to answer is, well, is this really a good and unbiased estimate for sigma x squared? And the answer is, of course, yes. And of course, we're about to go through the proof of that. But this will, of course, answer the common question, why do we divide by n minus 1 instead of 1 over n? And it dives into this particular question because this thing, even though it looks good, it's actually not an unbiased estimate for variance. Now, is it an estimate for variance? Yes, of course, that is true, but it is not an unbiased estimate for sigma x squared. Okay, so let's just go through the quick proof of that. Of course, if you're not interested in theoretical proof, you can of course skip this, but this proof actually has a few computational things that are actually useful for analyzing other properties that we're going to eventually discuss, right? So let's just prove that this s squared random variable is an unbiased estimator for sigma squared. So what is the expected value of s squared? Because if this is equal to sigma squared, then we're done with the proof. So the expected value of s squared is going to be equal to 1 over n minus 1 times the sum, so the expected value, so let's just write this out. So this is the expected value of 1 over n minus 1 times the sum from k is equal to 1 to n of xk minus x bar, the quantity squared. So first off, we can factor out this 1 over n minus 1 because that's just a constant, nothing fancy there. So we have 1 over n minus 1 times the expected value of the sum from k is equal to 1 to n of xk minus x bar, the quantity squared. The next thing we can do is switch the expected value in the sum, because the expected value of the sum is the same as the sum of the expected values. That's not fancy at all, so that's 1 over n minus 1 times the sum from k is equal to 1 to capital N of the expected value of each of these objects. Actually, you know what? I'm actually not going to switch those out yet. I'm actually going to FOIL this out, and I'm actually going to analyze that instead, because I think that's probably a lot easier. So that's going to be the expected value of the sum from k is equal to 1 to n. So let's FOIL that out and distribute the sum over that. So that's going to be the sum of xk, the quantity squared, minus 2x bar, the sum from k is equal to 1 to n of xk, plus the x bar squared times the sum from k is equal to 1 to n of 1. So there's a few algebra things that I've sort of skipped there, but hopefully you can fill in the details. So this term clearly is going to be the second moment. That shouldn't be too strange for us. Now, what are we going to do with this term? So that's, of course, the expected value, but we have the expected value of the expected values. It's a little strange to look at. So remember that x bar is going to be the sum of the x values divided by n. So that means we can replace the sum of x with x bar times n. So we can actually replace that in this particular expression. So once we have that, we're going to have 1 over n minus 1 times the expected value of, and then we have the sum from k is equal to 1 to n of xk, the quantity squared, minus 2n x bar, and then there's an x bar there. The n is coming from this replacement, and then we're also going to have another x bar. So it's going to be x bar, the quantity squared, and then plus n x bar squared. Now, where is this n coming from? Because we're having 1 plus 1 plus 1 plus 1 plus 1 n times, and that's, of course, equal to n. So that gives us that. So now let us distribute and rearrange our expected value, because again, the expected value of the sum is the sum of the expected values. So let's just see what that comes out to. So up to this point, we have that the expected value of the sample variance is going to be equal to 1 over n minus 1, and then we're going to have the sum from k is equal to 1 to n of the expected value of xk squared. So that's the second moment of each of those variables, and then we're going to have minus n e x bar squared. And why is that? So keep in mind we have x bar squared here, n of them, and we have negative 2n x bar squared. So if it helps you, you can sort of replace n x bar with, for example, like y. So we have negative 2y plus y, which is, of course, minus y. So that's pretty much what we're looking at there. And we've just distributed our ex bar, or our expected value, and we have this expression. Now, what are we going to do with this, and how does it sort of evolve into what we're sort of going for? So recall that the second moment of a random variable is always equal to the mean squared plus the variance squared, because the variance is always equal to the second moment minus the mean squared. So that's just a rearranged version of something that we already know. Also, the expected value of x bar squared, because we need to figure out what that is, again, is just going to be the mean of x bar squared plus the variance of x bar squared. But remember, we actually already know what the mean of x bar squared is. That's actually just equal to the mean of x squared, regardless of the distribution. And the variance of x bar squared is actually just equal to the variance of x divided by the sample size n, right? So we're bringing back those properties that we proved before in order to find a representation for ex bar squared. And we're going to be using that in that particular expression there. So that's some nice little algebra review. So what does that give us? So the expected value of the sample variance is going to be equal to 1 over n minus 1 times the sum from k is equal to 1 to capital N of mu x squared plus sigma x squared minus n times, so we're just replacing ex bar squared with this particular expression. The n is still chilling in front, so don't forget it. So then we're going to have mu x squared plus sigma x squared all over n. Okay, so what else do we have here? So we can distribute our n into this term. Notice the n's are going to cancel. That plus is going to change to a minus. And we're going to be summing up a bunch of constants. Therefore, we're going to have n of them, because it's like 5 plus 5 plus 5 plus 5 n times. That's just going to be equal to 5 times n. So it's just going to be that sum constant times n. So that's going to be equal to 1 over n minus 1 times, and let's also distribute that n into that expression. So n mu x squared plus n sigma x squared minus n mu x squared minus sigma x squared. We have some cancellations going on, which is actually very, very nice. And we have that. And notice what happens here. Remember where we came from once we started this little proof. Now we've come down to this, and you can start to see how this starts to unfold. Now remember, we're assuming that the unbiased estimator for s squared is 1 over n minus 1 times the sum of square differences. So this 1 over n minus 1, this constant, technically is unknown. So if we were to use 1 over n instead of 1 over n minus 1, then we would have that 1 over n sort of chilling there. But notice what that constant, in particular this one, needs to be in order for us to have sigma x squared as our answer. Because notice, sigma x squared is a common factor, so I can factor that out. So I have sigma x squared times m minus 1. The only way that this result comes out to sigma x squared, thus proving our result, the only way that this is going to be true is if this constant is equal to n minus 1. So if this constant were to be 1 over n, that means the 1 over n and the n minus 1 aren't going to cancel. Therefore, the estimate, I guess you could call it s star squared, equals 1 over n times the sum of xk minus x bar, the quantity squared. This is not an unbiased estimator for the population variance, because this 1 over n is not going to cancel with this n minus 1 term. So therefore, that sort of motivates why we divide by n minus 1. And if that is the case, that means the traditional sample variance term is an unbiased estimator for this particular population parameter. So is there a standard deviation or a variance of this sample variance random variable? The answer is yes, but we're not going to get into the proof because we actually have other ways of sort of dealing with the standard error associated to using s squared and associating to the estimate for sigma x squared. We'll discuss that in detail a little bit later, but now let us look at a couple other things in terms of review that are actually very useful in order to use these conclusions that we've actually come up with. So now let us assume that S is a sample of independent, identically distributed, normal random variables. So that's what pretty much IID stands for, independent. Identically distributed just means that the distributions of each of these variables are the same. So if they are normal, that means they all have the same mean and the same standard deviation. So what other things can we, build from this set of IID random variables? So if this is the case, then x bar, if we define it to be 1 over n times x1 plus x2 plus all the way down to xn, this is just a linear combination, so a linear combination of normal random variables. So remember that the linear combination of normal random variables also is normal. So that means x bar will also follow a normal distribution, right? And we also know the mean and the standard deviation of it, right? So the mean of x bar is going to be the same as the mean of x, and the standard deviation of x bar is actually just going to be equal to the standard deviation of x divided by the square root of n. So we've already looked at those things and some applications of it. Now, if x bar is a normal random variable, then we can actually get another result. So if zx bar is defined to be equal to, let's define it to be the square root of n times x bar minus mu x divided by sigma x, which is the z-score for x bar using these particular two properties, and that's pretty much where the square root of n came from. And keep in mind, this is mu x and sigma x, not mu x bar and sigma x bar, right? So make sure you work out those details if you haven't already done so. So if x bar is a normal random variable, that means this object will follow a standard normal distribution. Some people will refer to the standard normal PDF as the Z distribution. This is a synonymous name for the standard normal distribution or the Z distribution. So those are just a couple of properties that we have discussed before, but let's also discuss a few other properties, for example, about the sample variance and also the possibly the difference between means and the quotients of standard deviations, and maybe even the proportion of a population for some given criteria or category. So let's suppose that s squared is the sample variance. So s squared is a sample variance where, so what is the unbiased and good estimate for sigma x squared, that's going to be s squared. So s squared again is 1 over n minus 1 times the sum from k is equal to 1 to little m of xk minus the random variable x bar squared. Right? So if xk are standard, normal, or z random variables, then the mean of all of them, right, is going to actually be equal to 0, because remember, the mean of a standard normal distribution is 0, and the standard deviation is going to be 1. So that means we're going to have the expression s squared is equal to 1 over m minus 1 times the sum from k is equal to 1 to n of xk squared. So this is just the sum of standard normal random variables. Remember that this is a chi-square random variable, the distribution of it, as long as xk's are standard normal, which we're assuming they are. Therefore, if we divide that by some constant k, that means this will also be at least a stretched version of a chi-square random variable. So that means s squared will follow a chi-squared distribution with v equals, or nu equals, n minus 1 degrees of freedom. Right? So this is just some of the things that we explored before when we talked about, for example, the t chi-squared and f distributions some time ago. Now, a very important scenario is suppose we do not know sigma x squared, the variance of the population, and keep in mind that this is a number. Then the t-score of a random variable is given by t sub x bar. Let's assume it's the t-score for the random variable x bar. Is given by the square root of n times x bar minus mu x all over sx. So again, let's assume that x bar is a normal random variable. And also keep in mind that this is not a number, this is a random variable too. So this is going to be a chi-square random variable, or at least something related to it. So this is going to be a chi-square random variable because we're taking the square root of another chi-square random variable, and it's going to be, of course, stretched a little bit, but still it can be chi-square or approximated by 1. So we have a normal random variable divided by a chi-square random variable. What type of random variable will that introduce? Well, the notation of this is clearly going to result in a t random variable. So that means if x bar is a normal random variable, that means it's, sampling from a normally distributed population, and sx is sampling from a normal distribution as well, which of course, they usually come in pairs, or at least the approximations of them are. Then that means that tx bar will follow a t distribution with nu is equal to n minus 1, again, degrees of freedom. Because for each, degrees of freedom, we have a different t distribution and a different chi-square distribution. So you have to know the degrees of freedom in order to do these calculations. So let's also mention a couple other important things that we have discussed at this point, just to summarize. So notice that if x1 bar, so let's assume that this is a sample mean that's approximating some population mean mu1, and let's assume that mu1 is the mean of a normal distribution or a normal population. And let's assume that x2 is the approximation for mu2, which is the population mean of another population, or possibly the same population at a different time. So if x1 bar and x2 bar are normal random variables, then if we define x bar d as the difference between them, again, x1 bar, x2 bar, if these are normal, that means their linear combination will also be normal. So that means this also will be a normal random variable, provided that we know sigma 1 squared and sigma 2 squared. But what if we don't know sigma 1 squared and sigma 2 squared? So if we do not know sigma 1 squared and sigma 2 squared, then what else can we say? Well, x bar d, again defined to be x1 minus x2, will follow take a guess, a t distribution with question mark degrees of freedom. Now, I only say question mark degrees of freedom because it's not necessarily obvious as to what the value of nu will be, because the samples that x1 bar and x2 bar are representing need not be the same size. So do you choose the greater sample size, the less greater size, an average of the sample sizes, a weighted average of the sample sizes, -1 or -2? Like, what do you do for the degrees of freedom? We'll revisit that particular topic later once we actually do hypothesis testing on differences between means. But for now, at least know that the difference between them, if you don't know what sigma 1 squared and sigma 2 squared are, the difference of means will follow a t-distribution with some degrees of freedom, and we can figure out an approximation for that. So let's also just talk about, what if we don't want to compare the means? What if we want to compare the standard deviations? So since standard deviations are usually dealt with square roots and radicals, it's usually not practical to look at the difference between standard deviations, because the difference between standard deviations and variances could be negative, and that's going to cause some issues, especially with the chi-square distribution. So what we usually like to do, because if you have two positive numbers, if you multiply or divide them, they're also going to be positive. So let us define SQ squared to be equal to the quotient of the sample variances. So this S1 squared and S2 squared are independent chi-square random variables. Let's assume with V1, V2 degrees of freedom. So V1 is the sample size of sample 1 minus 1, and V2 is the sample size 2 minus 1. Then the distribution of SQ squared will be a F distribution with degrees of freedom pair V1, V2, which is going to be equal to N1 minus 1, N2 minus 1. Okay, so if we want to sort of test whether the variances between populations are same or very different, we would be using an F distribution here. And keep in mind, this is independent of what the means are, so we don't have to consider, like, is there like a T distribution version of the F distribution? No, we don't need to assume that. So what other metrics do we usually use in hypothesis testing and research studies? So let's ask this question. So what about the population proportion? Right? And this is related to, for example, the binomial distribution, or anywhere else where we use the probability of success as something in our calculations. So the population proportion, which we usually represent by P, is always going to be equal to x divided by m. So we're going to be using P as the parameter for the proportion of values in our population, capital P, where x is the observed number of successes, or the total number of successes, total number of possible successes all over the population size. Right, so that is what we call the population proportion. So if you're interested in the proportion of people in a population that are happy, you look at all of the people, you count how many people are happy divided by the total amount you have, and that quotient, that ratio, that percentage is what we call the proportion of the population that is happy. So if this is our population proportion, what are we going to estimate it with? So we're going to estimate with the sample proportion, P hat, which is going to be equal to x divided by little m. So what does x represent here? So this x is going to represent the total number of observed successes in our sample S, and n is our sample size. All right? So again, is this object an unbiased estimator for that object, we should be able to prove that. So the expected value of p hat is going to be equal to the expected value of capital X divided by n. Keep in mind this is actually the same as the expected value of 1 over n times x. 1 over n is a constant, so that means that's going to be equal to 1 over n times the expected value of x. Now what is the expected value of x? So x is the total number of possible successes. So what is the expected value of the number of total possible successes, or the total number of observed successes in a sample? That is related to a binomial distribution, right? So remember, the binomial distribution represents the probability of getting an observed number of successes out of a sequence of independent Bernoulli trials. So the expected value of x is actually going to be equal to n times p, and that's actually going to be equal to p, where p is actually the population proportion. So that means the expected value of p hat, the sample proportion, is actually equal to this calculation for the population proportion. Therefore, this is an unbiased estimator for that. Now, is there a standard error associated to this estimate? Yes, of course, because they're rarely going to be the same. So how do we go about finding that? So the variance of this estimate p hat is going to be equal to the variance of 1 over n times x. So again, 1 over n is a constant that can quadratically factor out. So we're going to have 1 over n squared times the variance of x. Keep in mind, x is a binomial random variable, so that's going to be equal to np times 1 minus p. One of these n's will cancel out with each other. So that's going to be leaving us with 1 over n times p 1 minus p. So that means the standard error associated to using p hat as an estimate for p, the population proportion, is going to be equal to the square root of p times 1 minus p all over n. Now this is a very, although nice looking formula, there is one slight caveat to it. Because remember, we're using p hat to estimate the population proportion p, but in order to find the standard error for p hat, we actually have to know what p is. So that sort of defeats the purpose of using p hat as an approximation for p. So what is a good approximation for this object? Take a guess. So remember, p hat is an approximation for p. Therefore, an approximation for the standard error for p hat is actually going to be approximately equal to p hat times 1 minus p hat all over little n. So this is the standard error, at least the starting point of a standard error, because this and approximation is not exactly equal to each other. There are some alternatives for the standard error formula, which we will discuss later. But that is just an introduction to point estimates and standard errors for statistics and parameters, and we're going to be using these a lot when we start doing confidence intervals and hypothesis testing. I hope you enjoyed this introduction, and I'll see you in the next video. Take care.